we are doing our PhD at the Institut de Ciències de l'Espai, located at the University of Barcelona, of the Autonomous University of Barcelona, sorry. So we are doing cosmology, and cosmology is the science that tries to understand the universe as a whole, what it's made of, and how it's the evolution of the universe. And the building blocks of the universe are galaxies, as you can see here. And through observations, we see that galaxies are moving away, they are separating. So this means that the universe is expanding, the whole universe. And gravity is the driving force that governs this expansion. And each pair of galaxies feels the attractive force of every pair of galaxies that you can imagine. And this force, since it's attractive, slows down the expansion. Also, gravity makes that galaxies want to be together. In this picture, we see a plot of the positions in the universe, of the galaxies in the universe. The Earth would be located below, and we are observing the universe. And in this plot, we show from above what we see. Every point is a galaxy, and as you can see, galaxies like to be together because gravity pulls them and puts them in regions to form these kind of funny structures. In cosmology, but we have a huge problem, is that only 4% of the content of the universe is made of the matter that we understand, of atoms. Atoms is what forms our planet, ourselves, the sun, the stars, galaxies. But to understand the picture I was showing you before, to understand from a theoretical point of view, we need to add more matter that we call dark matter. We don't know what is dark matter, so we put these funny names, and we need to understand what's this kind of matter. And even more strange is dark energy. Dark energy is another kind of matter that we don't know what it is, and it has a repulsive force that accelerates the expansion of the universe instead of decelerating. And at this point, it's clear that we need to understand what's going on here. So we used to have two sources of knowledge in astrophysics. One is theory, the other is observations, but nowadays we have a third one, that are simulations. Simulations consist of using a computer, put a physical system inside the computer, tell to the computer which are the physical laws that govern this system, and evolve it and see which solutions give us the computer to this system. And in cosmology, we do exactly this. We put how the universe was at the beginning, we switch on gravity and look how structures start to form. Matter fall to form these structures, and these are the structures we see in the universe. But these simulations are very expensive, computationally speaking. We need large supercomputers to perform these simulations. This is the Mare Nostrum supercomputer here in Barcelona, and need thousands of processors working in parallel during several weeks to do one simulation of those. But we want to do not just one simulation, we want to do many of them. Why? Because it's like a dice. A dice, if you roll it once, you have a result, but this is a statistical process, so you want to do it many times. And in simulations, we have the same situation. You want to do many simulations, and to do this number of simulations, you have to be fast. And we are now doing fast simulations that are less accurate, but you can do many of them, and my work consists of compare these different kind of fast simulations and see their performance. So, next speaker, this is Arnau.
So, as you probably see, we can study the distribution of galaxies in the universe from the observation from telescopes, and we can also study in simulations dark matter and galaxies and other things, no? That we maybe cannot see with the same precision in observations. But we need to understand how galaxies and dark matter connect between them, which is the relation between because our final goal is to try to measure and infer properties of dark matter from observations. So there are several ways to try to see this connection, and one of them is from clustering. Clustering is by studying how the galaxies and dark matter cluster because of gravity, no? And from this we can try to study the connection between galaxies and dark matter. So, and there are several ways to measure clustering. One way is by calculating the probability of finding, for a given distribution of objects, finding a neighbor in a given distance. So I will put a simple example here. We have in the top left, in the top left panel, we have a distribution of points or particles, and in the top right, we can see the measurement of the clustering. So as you see, these particles are organized in clusters of 10 units of size. So this means that there is a high probability of finding pairs separated less than 10 units. And because of that, the amplitude of the clustering measured at these distances is high. On the other hand, we can see that these clusters are separated 40 units between them. And because of that, there is a high probability again of finding neighbors at around 40 units between them. And because of that, we have a maximum at 40 in this measurement of clustering. This is an example, a toy example, where we can see that from the shape and amplitude of the clustering, we can learn about the distribution of these objects. And we can go to observations and measure the clustering of galaxies, and we can go to simulations and measure clustering again. And we can also study how the clustering depends on different properties, such as the mass of the dark matter, such as the luminosity of galaxies, the age of the galaxies, stellar mass, whatever, no? And it has been seen that at larger scales, the galaxies behave as tracers of dark matter. What does it mean? So to see the concept of tracer, we can go to Europe in these pictures in the top, and we can see that we can see light in Europe. We can see the light at night, and we can see that the light traces the population. So does it mean? This means that where there is more light, there are more people living there. So exactly the same happens in the universe. At large scales, where we have more light, where there are more galaxies, we have more dark matter. And this is very useful in order to understand the connection between galaxies and dark matter and use it for cosmology. But this is not enough. We need to know how exactly we can infer properties of dark matter and presence of dark matter from the properties and distribution and types, shapes of galaxies. And well, this is maybe mainly what I'm trying to do with my PhD by analyzing the clustering at larger scales. Thank you.